Welcome back, everyone, to CircleCityCon Track 3. Please welcome Alexei Kojenov with the talk, Break Crypto Like a Pro.
Thank you. Hi, everyone, and welcome to this talk. So let's just move on. Well, back in January, if you followed crypto news or even like security news, you could not miss this huge vulnerability that was discovered in Microsoft. It was, I'm hearing a little bit of static. I don't know if it's on my side or, anyway, I hope you guys can hear it. Okay, it's gone. Cool, thanks. All right, so this big vulnerability was in a cryptographic library in Windows, and that code was used to verify things like digital certificates, to validate code that was pushed for updates or that you could install, and the consequences of this would be pretty dramatic if this was exploited. And at this point, I don't know if this was exploited in the wild or not, but the issue was pretty huge. And I wanted to point out that the problem with this particular bug was not that it was an issue with any particular cryptographic scheme or algorithm. Microsoft used like the correct algorithm. They did pretty much everything right. They just made a couple of little mistakes in their code. And even though, like, I would say they had all the checkboxes checked, like, is this the so-and-so algorithm? Yes, check. Are we using the correct parameters? Check, yeah, and everything. FIPS certified, whatever, right? There was still an issue. And your cryptographic scheme is not just your algorithm. It's not just whether you using the correct library or whatever. It's the entire thing. If something is broken there, your entire cryptographic scheme is broken. And that was the case here. So you can still make, I mean, there's a lot of room for mistakes, and even very smart guys at Microsoft did it. So, okay, why this talk? Why did I bring that up? We all understand that cryptography is hard. I hope we can all agree on that. And mistakes are bad, right? The coding mistakes are not fun. And especially if those mistakes lead to some kind of security issues, we as security professionals know that these things are especially really, really bad. So let's just agree on that. So today we're going to be talking about how to exploit some of these mistakes. We're not going to talk about any 0 days. I'm not giving you any like new and juicy stuff. This is all pretty like known, but yeah, there will be no complex math. That's really not my intent today. We definitely not going to talk about any quantum stuff. This is not that talk. And we're not going to discuss how to break correctly implemented crypto, because by definition, correctly implemented crypto is unbreakable today. Might be breakable tomorrow, but today it's good. So I am a software developer, and in the past, I spent over a decade writing code, and then I decided to switch gears. Now I'm in security, mostly breaking things and helping people fix them. Well, I have a couple of security certifications, but this is the thing that I wanted to highlight. I am not a cryptographer. So I'm pretty sure that there are people here in this virtual room who know more about cryptography than I do, and that's fine. I do not pretend that I know everything here, and I'm coming to this particular topic from strictly practical perspective. As a hacker, as a security professional, what can I do to demonstrate a vulnerability, and what issues should I be looking for to like if I'm looking at the code, are there any things that my developers need to fix? And if I'm a developer, right, how do I do everything right? So just general recommendations. we all need to use well-known and secure algorithms, right? We no longer use MD5, we no longer use DES, and there's a reason for that. Now, okay, we picked the right algorithm, but now we got to pick the correct, good library, like meaning a good implementation of this algorithm. So we don't just download some obscure code and run it. We want to use some kind of library that's well maintained, that that does not have known issues and so on. And we definitely don't write our own implementation of cryptography for production. I mean, you can write it for fun, for studying. That's awesome, but I would not run my own code in production. Now, the next thing that's important to highlight is we need to follow the best practices. So if somebody is telling you that you need to use a good random number generator, or you need to use random IV for AES-256 algorithm, there's probably a reason for that. So all these best practices and guidelines are there because if we do not follow them, we open ourselves to potential problems. Yeah, and I've already said that we don't invent our own crypto, right? And you might have heard it before, so I'll be repeating. Okay, in terms of common mistakes in cryptography, we can put them in a few separate buckets. So first one would be insufficient entropy, meaning there's not enough randomness. And when there's not enough randomness, things get predictable. And in cryptography, that's not a good thing. When we look at ciphertext, meaning the encrypted code, encrypted data, it should all look like random data to us. We should not see any patterns, nothing like that. Because, like I said, if we start seeing patterns, things get predictable, and there is a potential for breaking something. The second common mistake is algorithm choice. So we don't use the correct algorithm for the purpose. We use a chainsaw where we need to use a hammer, or vice versa. So we need to understand what we're trying to do and what would be the right algorithm. The third one is, okay, we picked the right algorithm for the purpose, and now we don't really look into how to do it right. Like, okay, what kind of key do we need for that AES-256 algorithm? Where do we get it? Are there any other things that we need to tune in that algorithm specific to that algorithm? So that's also important. The fourth one is the message integrity. We often tend to focus on the confidentiality of things. So we want to encrypt so nobody decrypts, or we really care about keeping things secret, but we tend to forget that if somebody can tamper with the message, with the encrypted data, that's not good either, and that can lead to pretty bad things. And the last but not least is the key management. You can do everything else right, but if you don't manage your keys correctly and they get leaked, your entire scheme is broken. All right. This is the math for today. We're only gonna talk about the single operation called exclusive OR, or XOR. You should know this one, right? But I call it the ultimate crypto weapon, and the reason I'm doing that is I'll show you why. There will be a few demos today that will show us how you can use XOR to break things in crypto. There are a few properties of this particular operation. First one is anything XOR 0 is the same thing. So 0 does not change things. If you XOR something with itself, you'll get 0. So basically it just cancels itself out. And then A XOR B, if A XOR B equals C, then A XOR C equals B, and B XOR C equals A. So basically you can move these values to either side of the equal equal sign, and everything will be true. And that's a cool thing about XOR operation. All right, the next thing that I wanted to discuss is the randomness. Like I said, it's very important in cryptography. And we have two major types of random number generators, RNGs. True random number generator is a generator that's usually hardware based. It gets entropy from the environment, maybe fluctuations in temperature or electricity or ambient noise or whatever. These random number generators are non-deterministic and completely unpredictable. So you cannot guess with high probability what the next generated value will be. Is it going to be 0 or 1? Well, no idea. The problem with true random number generators is they are not fast. They're pretty slow. So we have another kind of random number generator. It's called pseudorandom. These are deterministic and seed-based. Basically, pseudorandom generator is an algorithm. You seed it with a number, with a value, and it generates a stream of bits and bytes that looks like random, but it's completely dependent on that initial seed. So and it's repeatable. So if you give it the same seed again, it's going to generate the same pseudo-random stream. Well, you might say this is not really good, but that's actually, in most cases, that's sufficient for the purpose. And a lot of times we see a combination of both things being used. First, we use true random number generator to get that seed, and then we seed the pseudo-random generator with that true random number, and then we get a pseudo-random stream. All right, and with that, let's talk about mistakes. 5 years ago, some people decided to write a ransomware Trojan for Linux. At that time, the ransomware was already very popular, but it was mostly targeting Windows platforms. So some people decided, well, Linux runs the internet, so why don't we just ransomware that platform and get rich? But well, they made a mistake, and the first version of this malware completely failed because it used predictable encryption keys to encrypt the data, and anybody could decrypt them without paying ransom. So let's take a look at how that can be done. Here's some sample code. Oh, by the way, all the code is on GitHub. And at the end of this presentation, I'm going to give you a link, and you'll be able to download it, play with it, modify it if you want, and just study. But it's all pretty basic, all pretty simple. So this code generates a random key, right? And then it opens the file, encrypts it, and demands to pay the ransom. But yeah, that's pretty much it. And the key is not really stored anywhere. It's thrown away. So, but the thing to note here is we seed that random number generator with the current timestamp. All right, that might be okay, but if you run it, we have just encrypted file, and the encrypted version is completely like binary data, no way to understand what's going on. The original file was text. Here it is. The text says not all random functions were created equal. Okay, and like I said, the key is not stored anywhere, but we know that this the encryptor was using the current time. So to decrypt, we just need to get this file modification timestamp and seed our random number generator, and we'll get the same exact key to decrypt it. Let's see if that works. Yeah, and it did. It successfully decrypted the file and printed the original data here. Cool. That was really, really simple, but like I said, people make these mistakes, and in this case, those ransomware guys did it. Yeah, so a reminder to everyone, you cannot just use time to seed your pseudorandom function. You need to use MD5 of timestamp. Well, of course, this is a joke. Don't do it. It's really bad advice. All right, let's move on. Okay, let's talk about encryption algorithms. A very simple but very, very secure algorithm, one of them is called one-time pad. Let's say we have a message that we want to encrypt, and we have a key. So our encryption is actually a simple XOR operation. We just XOR that message with the key, and that's it. That's our ciphertext. And decryption is the opposite. When we XOR the ciphertext with the key again, we'll get the original message back due to the properties of the XOR operation. And here is an example. Well, all right. Now, one obvious problem here is that your key has to be as long as your message. So if the message here is 7 bits, your key has to be 7 bits. If your message is 1 gigabyte, your key has to be 1 gigabyte. So it's very, very impractical. One-time pad is not, I mean, the key management is a nightmare. The other issue with this algorithm is in the name. It's called one time for a reason. And it means that you should not reuse the keys. So let's see what happens when you reuse the keys. Let's say you have a message 1 and you encrypt it with the key. And you have message 2 and you encrypt it with the same key. And by encryption, I mean you just XOR, right? Now, if we we have 2 ciphertexts, but if we XOR these 2 ciphertexts, this will expand to this expression, and the key will cancel itself out. And as a result, we get an XOR of the original messages. So the XOR of ciphertext is the same as XOR of original messages. And you can guess that this is not good. Like I said, when you can derive some predictable results from cryptography, then things can go really bad. All right, you might ask, okay, so what? We still don't see the original message here, but we get the XOR. And in many cases, that would be enough to either break things completely or get some really good guesses about the original message. So do not reuse the keys. Okay. Stream cipher is otherwise called more practical one-time pad because it is based on one-time pad, but stream cipher is using a different kind of key. So instead of this huge long key of the same length as the data, we use a finite key and we use a generator function to generate a key stream. So the original key might be, let's say, maybe 16 bytes. And then we basically seed that generator function, and it will generate us an infinite stream of pseudorandom bits that we can just use in the stream cipher. So the encryption is the same as in one-time pad. We just XOR the message with that key stream, and the decryption is the same operation. But again, do not reuse keys here, because if you give the same key to this generator, you'll get the same exact pseudorandom byte stream, bit stream, whatever. And yeah, that's not good. Okay, so let's see in practice how we can break and this scheme and decrypt the message without the key. All right. I have two pictures here. One is a picture of myself, and the other is a picture of this black and white smiley face. And I'm going to encrypt both of these pictures using my special encryptor, encrypt image. What it's doing, I'm cheating a little bit here. So I'm not encrypting the file itself. I encrypt pixel by pixel to give it more, so it's more visual for us, right? So I encrypt those pixels, and I get, these random noise pixels. This is the result of encrypting my picture, and this is the result of encrypting that smiley face picture. Both look really random, right? But I'm encrypting with the same key. And in this case, I'm using, if I remember correctly, here it is. I'm using RC4 algorithm, which, by the way, is no longer secure, but I'm using this here just for demonstration. The idea is the same. Okay, now, well, we have these two encrypted images. Can we do something with them? Well, let's fire up a graphics editor. Takes a while. Okay, cool. And all right. And open both images in that text in the graphics editor. So here's the. So I have two layers in this image. The first layer is the encrypted image of me. The second layer is encrypted image of the smiley face. Well, both look random again, but this particular editor allows me to perform layer operations. And one of them is XOR. I don't know if you can see it well or not, but here, XOR. I'm not lying. Now let's see what happens if I do XOR. Boom. Immediately, we can recognize both of the original messages. We can see that one of the original data was a picture of a human, and the other original data was this smiley face, whatever, right? So we, with our image recognition capabilities, can immediately decrypt both original messages in this case, and that's just that's just a result of XOR operation. Now, what if we take it further? What if we know one of the original messages? What if we know that one of them was this smiley face? Now, if we add that as another layer and apply XOR operation, we get the other original message as is, without any changes, without any noise, without anything. So let's recap it again. We have three layers here. One looks like random. The other looks random. But when we combine them all with a very simple XOR operation, we get something really cool. Okay. In addition to stream ciphers, we also have block ciphers. So stream ciphers operate on bits. You can encrypt bit by bit. Block ciphers operate on blocks. And popular block size these days is 16 bytes. But and it can vary depending on the algorithm. But the block cipher is taking the entire block, is taking the key, and then it does permutations and gives you the result, which is the encrypted data. Again, it needs the whole block in order to work. Now, your message is usually not 16 bytes. It's usually longer, some kind of a file, some kind of data. So what happens when we need to encrypt longer data? Well, the most obvious and most straightforward way to do it is to encrypt each block separately and then combine the results. So we encrypt the first block with the key, second block with the same key, third block with the same key, and then we just have the result. The problem here is if block 1 and block 3 are the same in original message, they'll be the same in the encrypted message. So you'll see a pattern here. And even though the data will be encrypted, sometimes those patterns are enough to break the encryption. So let's see how we can see the plain text in the ciphertext. And again, I am using a visual example here. Here is a test image that's a snapshot of my title slide. Okay. And I'm going to encrypt this image with my special encryptor. And it didn't work. That's very cool. I have not seen this before. Oh, interesting. Okay. And I'm sorry about that. I should have prepared better. I did not account for the block size. Okay. All right, let's skip that example. But the idea here is when we encrypt, we'll be able to see the pattern in the encrypted image, and we'll be able to recognize the original message. Okay. So a better way to do it is use a different mode with the block ciphers. So if we have these consecutive blocks of the plain text message, we can then use we basically use the previous block to seed the next block. So let's start with the last block here. Before we perform our encryption operation, we XOR our plain text block with the ciphertext from the previous operation, and that will give us more randomness. This will actually give us a lot of randomness, and the result of our ciphertext, even though this plain text block was seen before, it will be completely different from anything that we have seen before. Now, what about the first block? It did not have a previous one, but we still need to XOR it with something, and that's how we introduce the initialization vector, or IV. IV is just a random block. It's not a secret data. It just has to be random. Each encryption operation, you generate a new IV, and you just store it with the data. And like I said, it does not have to be secret. It just has to be random. Okay, how does the CBC encryption decryption work? So if we have the encrypted message, the ciphertext consisting of 3 blocks, then we will decrypt the first block, and then we XOR it with this initialization vector. The second block will decrypt, and we'll XOR it with the first block ciphertext, and so on. Okay, that's fine. Now, some people think, and that's a mistake that I want to talk about. Some people think, okay, I have the key that I know it is secret, and I need this initialization vector. And why can't I just use the key as IV? That might seem like a good idea, especially in if you're dealing with legacy code that you're trying to change the encryption algorithm, and you don't have a field, you don't have a room to store the initialization vector. So I'll just use the key. It's random enough. From the attacker's perspective, they don't know my key. It's random. Since both the sender and receiver know the key, I don't have to store it with the data, so it's not going to be leaked. All right, but it's actually not very good, because let's see what happens when we decrypt this kind of message. So again, we have an encrypted message consisting of 3 blocks, C1, C2, and C3. If an attacker can modify the encrypted message and give it to the decryptor and get the result back, something really unfortunate can happen. So I, as an attacker, can build a new message. I'll take the first cipher text block and just copy it. For the second block, I just use all zeros. All my 16 bytes are going to be zeros. And we'll see why I'm doing that. And for the third block, I'm copying the first block again. Okay, why? Well, let's see why. When we decrypt this first block, it will basically be an XOR operation of the decryption and the key, because as we remember, we have just used the key as IV, right? The second decryption we don't really care about, but what we care about is those zeros in the ciphertext. So the result of the third block being decrypted would be that block decrypted XOR 0, which, as we know, 0 has no influence on the XOR operation. So the first block decryption and the third block decryption, you can already see that there is an issue. If we XOR these two things, we'll get the key. So the key is actually leaked in this scheme under certain assumptions, of course. Like I said, as an attacker, we can modify some things, the decryptor will decrypt them, and so on. But we sometimes we use these assumptions in cryptography based on the application where the cryptography is used. And so let's see one of such applications. This time, I need to find my browser. Here it is. So this time I have a web application that is using a session cookie. So first time I go into this application, it gives me a session cookie of a guest. And for convenience sake, I'm printing that session cookie right here on the web page. But here is the actual value of it, and it is encrypted. So I, as the user of this application, don't know the key to encrypt or to decrypt this session cookie, but the application knows it. If you look at the source code, the key is generated once and is stored in the file and is used for all the sessions. And like I said, we have no idea what the key is. But we know that we can modify this value, right? And we can give it back to the application, and it will print the result here. So here's our assumptions. So first thing that we need to do is we need to forge a new cookie with those zeros in the middle. And you see those AAAs, these are zeros in base 64. Now, when we give it to the application and refresh the page, it struggled with it because the message is no longer valid. It decrypted to some kind of junk, but that's okay. We need this. Here is this base 64 value that got decrypted. Now, if I give it to my other script to analyze that result of the decryption, it was able to derive that the encryption key itself. It reads C4, F1, whatever. Now, if I go and actually print that session key file where the web application is storing that session key, you'll see that it will match exactly. It's C4, F1, E0, FB, and so on. So again, just by using this application, seeing the result of decryption, being able to modify encrypted data, we were able to completely crack the encryption key. All right, another thing with the block ciphers is so-called padding. As we discussed, the block ciphers work on blocks, and it expects, like, let's say if it's AES algorithm, it will expect 16 bytes, right? But your data is not necessarily, the length of your data is not necessarily a multiple of 16 bytes, right? It's not exactly 16, 32, 48, and so on. Here is a message of 10 bytes. How can we deal with it? The block cipher is not going to like it. Okay, so what we do is we add the missing 6 bytes to get 16 bytes. And by convention, we set each byte to 6. So the system knows that 6 bytes were missing, and this is just padding. They all look the same, and they can be thrown away when needed. And that's cool. Now the block cipher can encrypt this. On decryption, what happens is we need to check that padding. We need to assume that the pattern is correct. And if we see something wrong here, like going back one slide, if one of these bytes is not 6, or if it's something else, then this is wrong padding. By convention, there's something wrong. The data was corrupt. So it will be an error condition. And it's pretty fair to assume that we need some kind of error message. So if padding was OK, then we'll continue. If it was not OK, we'll print error message. But the problem here is if we do that and let the user know that the padding was incorrect, it can lead to pattern oracle attacks. And the pattern oracle attacks were completely on the attacker being able to modify the message, giving it to the decryptor, and then the decryptor letting the attacker know whether the padding was correct or not. And there was no other information that we can get from the decryptor. And that can completely break the scheme and retrieve the original message. And I have a working version of pattern oracle in a web application. So here's our application. This web app has one endpoint with a parameter, which is an encrypted message. And when we give that encrypted message to the app, it tells us that thank you, I'll get back to you soon, whatever. It might store it somewhere. So here's an example of such encrypted message, and the application just gave it to me. I have no idea what it is, right? But if I modify one of the bytes here, so let me modify the last byte. It was 4. I'm going to set it to 1, and resend that message. I get an error saying invalid message, which suggests that the padding was incorrect. I have just modified that last byte, and the probably last block decrypted to some garbage, and the application was not able to deal with it. Okay. Again, we just have this URL. We have this encrypted message. We have no idea what that is. Let's try to break it. My exploit script just accepts that URL and analyzes it and tries that pattern oracle attack by modifying bit by bit and sending multiple requests to the server, hundreds, I don't know, maybe thousands. I never counted, but let's see what happens. So it sends those requests, and if I look at the back end, sorry, the font is a little small, but you can see it in the web server log. It received hundreds of requests, and each one of them, they look pretty similar pretty identical, but there was one difference somewhere. One byte of this message was different. But let's see what happened. We were able to completely decrypt the original message, which reads padding oracles are real. Let's look at our code. The code, the server code, yep, it encrypted this message. And that's it. I mean, it encrypted message, gave it to us. Here is the exception handling where the padding was incorrect. As a matter of fact, it just uses the generic exception. We don't, like in this case, we don't even know whether the padding wasn't correct or something else, but most likely than not, it was incorrect padding because encryption operation, decryption operation will deal with any kind of binary data, and it doesn't really care. Okay, so far we, in the examples that we have seen, all the issues that we have seen were due to the bad integrity of the message. So we modified something, we gave it to, as an attacker, we gave it to the application, and it just swallowed that without checking whether the message was tampered with or not. So right there, we already see that how bad integrity can lead to bad things. But can we take it further and not just modify the message so it's garbage, but modify it with specific purpose? So let's say I send a message, send $100 to Alice, I encrypt it, and then the attacker intercepts that, modifies the encrypted message, right? And then whoever is receiving that message decrypts it, and they get a completely different result. So instead of $100 going to Alice, it's going to go to Mallory. Is this possible? As a matter of fact, it is. And let's see two examples, one with stream cipher and one with block cipher. The attack here is called bit flipping. So let's say our original message was guest. Again, we might be talking about session cookie, and our user is guest. So the encryption, and this session cookie is encrypted. The encryption is a simple XOR operation. Now, as an attacker, I can create a new session cookie, and I take the original one, and I XOR it with the original message. I know that I'm guest, but I also XOR it with the one that I desire to have. I want to be admin. Okay, cool. And I give that session cookie to the application, and it tries to decrypt it. And decryption is a simple XOR operation, as we already established. So this will expand to this kind of thing, and then that will in turn expand to this, and then guest and guest will cancel out. The key stream will cancel out, and as a result, we get the admin. So decrypting this message is completely predictable in this case. So let's see it in practice. I need to delete this session cookie and get a new one. Okay, here is our application. Again, it's using a session cookie. It's encrypted. It's a different encryption format. In this case, we're using a stream cipher. We are using Salsa 20. Salsa 20 is a pretty new, well, it's new, and it's secure algorithm. It's using a random nonce. So the key reuse is not an issue here as much as in, let's say, RC4. But we're not talking about key reuse right now. We're talking about modifying the message. So there is no integrity check. It just receives the cookie value, decrypts it, and then analyzes it, seeing if the user is admin or not. And let's see if we can break it. Okay, my exploit script is accepting the ciphertext and original plain text. And we know the original plain text here. It's conveniently printed on the screen, but I can also get it by looking at the source code, right? The only thing I don't know here is the encryption key itself. So the source code is open, but it's useless if I don't know the encryption key. But we can probably break it. Now, I need the desired plaintext. So instead of guest, I want admin. The other thing to note here is this application does not care about the second parameter, date, at this point. It's not currently being used. So we can just completely erase it and just leave the user information here. And we're going to replace guest with admin. And I forgot the closing brace. OK, this is better. So here is our new cookie value. Let's put it in the browser, send it to the app, and now we are admin. So this is the decrypted value. Now, again, we were able to modify the ciphertext without knowing the key, but we knew the original message, and we were able to change it to something that we want. That was pretty easy to do. Apparently, this same kind of attack is possible in block ciphers as well. Especially if we are talking about the first block. So the first block, as we know, is completely dependent on this initialization vector which is XORed with the ciphertext. And I'm just gonna give it to you as homework to analyze it, but it's basically the same idea. So we just modify the initialization vector with particular data, and when it's XORed during decryption, we get the desired results. And I have a demo for that as well, and you can play with it if you want later. So to fix this kind of issues, we need some kind of way to check the integrity of the message to make sure that it has not been tampered with. And that introduces the concept of authenticity and authenticated encryption. So with authenticated encryption, not only we get the ciphertext, we only get the authentication tag. And during decryption, we validate that authentication tag. And if it doesn't match our decrypted message, then we can conclude that message has been tampered with and it's not good. We just need to throw it away and give some kind of error, But like I said, we tend to focus on confidentiality a lot, and for a good reason, and that's all cool. But if there is no integrity, then there's no confidentiality either. Many attacks would rely on the fact that the integrity is not validated, that there is no authenticity in cryptographic scheme. Okay, and the last topic for today is storing passwords. 3 simple rules. Rule number 1, no plain text passwords, right? We know that. Rule number 2, no decryptable passwords. So if you store passwords in the database encrypted with AES-256 algorithm, we got to store the key somewhere. So if that key gets leaked, somebody can decrypt the passwords. Not good. And rule number 3, no one-way hash. And at this point, you're going to say, Alexei, are you kidding me? Everybody is telling me that you got to use one-way encryption to store passwords. Well, yes, that is correct. But some people take this literally, and they use a hash function instead of something else. So what is this something else? Something else is the key derivation function. Now let's compare the two here. So the hash itselth, like SHA-256, is cheap. It's fast, right? It's a very, very fast function for a reason. You want to calculate hashes quickly. Key derivation function, on contrast, is expensive. It can be expensive in terms of time, CPU usage, or memory, or all 3 at the same time. And it's designed this way for a purpose. So it's expensive to check the password. And that might sound like an issue, but it's not. If you're a user who's typing the password, you might be you won't make a big deal if you see like 200 millisecond delay or whatever, or even half a second delay when your application verifies your password. It's not a big deal. But for an attacker who tries to brute force your password, that's a huge deal. They are not able to brute force as efficiently as if you were using a hash function. So let me just give you a very small demo. I have a script that generates a couple of hashes. So the first time it's going to generate a SHA hash of my password, and the password is not revealed here, it's just a hash, right? Now I can run John the Ripper, which is the brute force tool, and it's comparing against the dictionary, and in the dictionary I have the word Pink Floyd, which appears to be my password, and it was able to crack it immediately. It tells me that it was able to check 84,000 passwords per second. Pretty impressive. But now if I do the same with pbkdf2, which is one of the key derivation functions. By the way, it's not the latest and greatest anymore, but it's still much better than SHA. And now if I run John the Ripper, first of all, it fired up 8 threads, and now it's taken much longer to analyze that hash, to try all these different passwords, to brute force it, and it's going to return eventually, but you can already see that it's taking much longer. So this is just a good example to show, how different that password cracking is, depending on the function that is being used. So in this case, it was able to only check 44 passwords per second versus 84,000. That's a huge difference and not very efficient. All right, so takeaways. If you're a breaker, you need to understand the concepts, those cryptographic concepts at some kind of technical level. You might need to go deeper a little bit in order to see what's actually going on, how can I break it? Examine the industry guidelines to understand why they're there and what can go wrong if those are not being followed. And expand on other people's work. There are tools, there are sample code, there are write-ups from CTFs or real-life vulnerabilities, and those are pretty cool to study and understand how things were broken. If you're a builder, again, you need to understand the concepts of cryptography and your task, right? Do use the right tool for the purpose. That's important. And then again, you got to know those guidelines and you need to follow them. Like I said, they're there for a reason. And learn from other people's mistakes. Read those about those vulnerabilities and see how things gone bad and try not to do the same thing. For further learning, I would highly recommend this course on Coursera. It's free and it's really amazing. And there's this online book. It's basically PDF, but very, very helpful. Lots of cool stuff for both breakers and builders. Like I said, my code is on GitHub. Feel free to download it, play with it, modify it, use it in your presentations, and feel free to contact me if you want to stay in touch. And thank you very much, and good luck.
Thank you. We will take an hour break and we'll come back here for our next talk. If you have any questions, please join the Discord in track 3. And thank you again for your talk.
All right. Take care, everyone. Bye.